$93 billion. Say that number out loud. Let it sit in the air for a moment. $93 billion, the equivalent of funding every public school in the United States for an entire year. The equivalent of rebuilding the city of New Orleans after Hurricane Katrina more than 30 times over. The equivalent of launching, operating, and maintaining the most ambitious scientific infrastructure in the history of our species. That is the number NASA has spent, adjusted for inflation across 7 decades, on one singular, relentless pursuit. Not a weapon, not a war, not an empire, the universe. And yet, there is a question that almost nobody dares to ask out loud, because the moment you ask it, you realize it cuts to the very heart of what it means to be a civilization capable of looking up at the night sky. The question is this: after 50 years of space telescopes, planetary probes, deep space missions, gravitational wave detectors, and over $200 billion in combined global space science investment, what exactly did we find? Not what we hoped to find, not what the science fiction writers promised us, what we actually found. The answer is simultaneously more humbling, more terrifying, and more extraordinary than almost anything the public has been told. 50 years ago, the United States government made a decision. It was not a dramatic decision announced in a stadium or broadcast in a fireside address. It was a budget line, a commitment, a slow, grinding, bureaucratic agreement to point the collective intelligence of thousands of engineers, astrophysicists, mathematicians, and mission planners at a problem so large that no single human mind can fully contain it. The problem of cosmic origin. The problem of scale. The problem of whether the universe we inhabit is unique, random, or governed by physical laws so precise that their precision itself demands an explanation. NASA was founded in 1958, born directly from the geopolitical pressure of Sputnik and the Cold War. But its scientific soul, its deeper, slower, more philosophically serious mission, emerged in the decades that followed. The Apollo program put boots on the moon and consumed the agency's identity for an entire generation. But the moment the lunar missions ended, something shifted. The engineers who had mastered orbital mechanics and life support systems turned their instruments outward. Not toward the moon, not toward Mars, toward the edge of everything. The Voyager probes launched in 1977. 2 spacecraft, each weighing roughly 815 kilograms, about the weight of a large dairy cow, were flung out of Earth's gravitational influence using a rare planetary alignment that occurs only once every 176 years. Mission controllers at the Jet Propulsion Laboratory in Pasadena, California, calculated that this gravitational slingshot, using Jupiter, Saturn, Uranus, and Neptune in sequence, would allow both probes to reach escape velocity from the solar system itself. They were right. Voyager 1 is now approximately 23 billion kilometers from the Sun, so far that a radio signal traveling at the speed of light, 300,000 kilometers per second, takes over 21 hours to make the one-way trip between the spacecraft and our ground stations on Earth. Think about that distance in human terms. If you drove a car at 100 kilometers per hour without stopping, no sleep, no fuel breaks, no mechanical failure, it would take you over 26 million years to reach Voyager 1's current position. The probe has been traveling since the year the first Star Wars film released in cinemas. It has outlasted the Soviet Union, the analog era of television, and the entire lifespan of the personal computer industry, and it is still transmitting. The signal it sends back is roughly 20 watts, the brightness of a standard refrigerator light bulb, from 23 billion kilometers away. That signal carries scientific data, measurements of particle density, magnetic field orientation, and plasma wave frequencies in a region of space called the heliopause, the boundary where the solar wind from our sun finally yields to the interstellar medium. No human-made object had ever crossed that boundary before Voyager 1 did in 2012. The data it sent back forced physicists to revise their models of how our solar system interacts with the rest of the galaxy. The heliopause was shaped differently than predicted. The particle densities were wrong by a factor of 40 times denser than expected, a correction that immediately changed how scientists model the interstellar radiation environment, which in turn affects every calculation about how life-bearing planets might be shielded or not shielded from high-energy cosmic rays. This is the pattern. This is the deep structure of 50 years of NASA science. Not triumphant confirmation of what we already believed. Constant, disorienting, productive revision. The Hubble Space Telescope launched in 1990. Its primary mirror had a spherical aberration, a manufacturing flaw of just 2.2 micrometers, roughly 1/50th the width of a human hair, that rendered its images blurry and nearly useless. Congress was furious. The press called it a national embarrassment. NASA spent $194 million on a servicing mission in 1993 to install corrective optics. The repair worked, and the repaired Hubble went on to measure the expansion rate of the universe with a precision that revealed something so bizarre, so structurally destabilizing to the standard model of cosmology, that the two physicists most responsible for the discovery received the Nobel Prize in Physics in 2011. The universe is not merely expanding, it is accelerating. Something is pushing galaxies apart, faster and faster, against the force of gravity. We do not know what this something is. We have named it dark energy, a placeholder, a confession of ignorance dressed in technical vocabulary, and current estimates suggest it constitutes approximately 68% of the total energy content of the observable universe. The thing that dominates everything. The engine behind cosmic acceleration. The force reshaping the fate of every galaxy cluster, every star system, every atom of hydrogen drifting in the void. We have no confirmed theory of what it is. This is what $93 billion bought. Not answers that close questions, answers that open abysses. The James Webb Space Telescope, NASA's most expensive and technologically complex scientific instrument ever constructed, represents over $10 billion in investment, a 30-year development timeline, and the coordinated labor of more than 20,000 people across 14 countries. It launched on December 25th, 2021, folded inside an Ariane 5 rocket like an origami letter from humanity to the cosmos. Its primary mirror is 6.5 meters in diameter, more than 2.5 times the collecting area of Hubble, and is composed of 18 hexagonal gold-coated beryllium segments that had to unfold in space with sub-millimeter precision after launch. The telescope operates at a temperature of negative 233 degrees Celsius, just 40 degrees above absolute zero, the theoretical minimum temperature at which all molecular motion ceases, because it must detect infrared light from objects so distant and so ancient that their light has been stretched by cosmic expansion into wavelengths invisible to human eyes. In its first year of science operations, Webb captured light from galaxies formed less than 350 million years after the Big Bang. For context, the universe is approximately 13.8 billion years old. These galaxies formed when the cosmos was roughly 2.5% of its current age. The images are not photographs in any conventional sense. They are historical records, time machines made of mirrors and mathematics. And what Webb found in those ancient galaxies immediately created what astronomers are calling a cosmological crisis. The galaxies are too big, too structured, too mature. According to the Lambda CDM model, the standard model of cosmology that has governed our understanding of large-scale structure in the universe for decades, galaxies of that mass and complexity should not have been able to form that quickly after the Big Bang. The physics of gravitational collapse, gas cooling, and stellar formation simply do not permit it under the standard model. And yet there they are, bright, massive, structured, staring back at us from the edge of observable time. The question is no longer whether Webb is calibrated correctly. Multiple independent analysis teams have verified the data. The question is whether our foundational model of how the universe grew from a formless plasma into the structured web of galaxies and filaments we observe today is, in some critical way, incomplete. Not wrong, necessarily, incomplete. There is a profound difference between a theory that is wrong and a theory that is missing something. A theory that is wrong collapses. A theory that is missing something evolves. The history of physics is almost entirely the history of the second category. Newton's mechanics were not wrong. They were incomplete, missing the relativistic corrections that Einstein provided. Einstein's general relativity is not wrong. It is likely incomplete, missing the quantum mechanical description of gravity that no physicist has yet successfully constructed. Every instrument NASA has ever launched has, in some way, accelerated this process of productive incompleteness. Every measurement that confirmed a prediction was valuable. Every measurement that contradicted a prediction was transformative. The $93 billion did not buy certainty. It bought precision. And precision, in science, is far more dangerous. Because when you measure the universe with enough precision, the universe stops behaving the way you expected. What happens when the most sophisticated observatory humanity has ever constructed looks back to the beginning of time and finds something that should not be there? The number that broke cosmology was not discovered in a single dramatic moment. It accumulated. Data point by data point, across two independent research teams, working in parallel competition through the mid-1990s, neither aware that the other was closing in on the same impossible conclusion. The year was 1998. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, had both spent years cataloging a specific type of stellar explosion called a Type Ia supernova. These are not ordinary explosions. They are, in the language of physics, standard candles, objects whose intrinsic brightness is known with enough precision that astronomers can calculate their distance purely by measuring how dim they appear from Earth. The dimmer the supernova, the farther away it is. The math is clean, the physics is reliable. Type Ia supernovae detonate when a white dwarf star, the dense burned-out remnant of a sun-like star, accumulates enough mass from a companion star to cross a critical threshold of approximately 1.4 solar masses. At that precise limit, called the Chandrasekhar limit, after the Indian-American astrophysicist Subrahmanyan Chandrasekhar, who calculated it in 1930, the white dwarf undergoes runaway nuclear fusion and detonates with a peak luminosity roughly 5 billion times that of our sun. 5 billion suns, briefly. Then silence. Because every Type Ia supernova reaches nearly the same peak brightness, they function as cosmic rulers. Measure how bright one appears from Earth, calculate the distance, then measure the redshift of its host galaxy, the degree to which the galaxy's light has been stretched toward the red end of the spectrum by cosmic expansion. And you can determine how fast the universe was expanding at the time that supernova exploded. Both teams expected to find the same thing. A universe expanding, but slowing down. Gravity, pulling all matter back toward itself, should have been decelerating the expansion left over from the Big Bang. The question both teams set out to answer was simple. How fast is the universe slowing? The data said it was not slowing. It was speeding up. The distant supernovae were dimmer than they should have been, not by a small margin of measurement error, but systematically, consistently, undeniably dimmer, which meant they were farther away than any decelerating universe could place them, which meant the expansion of space itself had been accelerating for at least the past 5 billion years, pushed by a force or energy component that no existing physical theory had predicted and none could explain. Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics in 2011 for this discovery. The citation described it as one of the most surprising findings in the history of cosmology. That is Nobel Committee language. In the unguarded conversation of physicists at conferences and in departmental hallways, the reaction was closer to vertigo. The component responsible for this acceleration was named dark energy. The name is not a description. It is an admission. Dark, because it neither emits nor absorbs light and therefore cannot be directly detected. Energy, because its effect on the geometry of space-time is consistent with some form of energy density uniformly distributed throughout the vacuum of space. Current best measurements, primarily from the Planck satellite's mapping of the cosmic microwave background radiation, place dark energy at approximately 68.3% of the total energy content of the universe. Ordinary matter. Everything made of protons, neutrons, and electrons, every planet, star, gas cloud, and human body, accounts for roughly 4.9%. The remaining 26.8% is dark matter, a separate mystery entirely, detectable only through its gravitational effects on visible structures. Run those numbers again. 4.9% of the universe is made of the stuff we can see, touch, and measure directly. The remaining 95.1% is composed of two things we cannot directly detect, cannot explain from first principles, and have no confirmed theory to describe. The universe is, in the most literal scientific sense, almost entirely unknown. This is not a philosophical statement. It is an empirical one. And it is the foundational crisis that defines modern cosmology, the discipline that NASA's most expensive instruments have been built, launched, and operated to address. The cosmic microwave background radiation is the oldest light in the universe. It was released approximately 380,000 years after the Big Bang, at the moment when the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms for the first time, a transition called recombination. Before that moment, the universe was an opaque plasma, so hot and dense that photons could not travel more than a short distance before being absorbed and re-emitted. The universe was effectively opaque. At recombination, the plasma cleared. Photons streamed freely in all directions for the first time. Those photons are still traveling. They fill the universe uniformly in every direction, arriving at our detectors as microwave radiation with a temperature of 2.725 degrees Kelvin, 2.725 degrees above absolute zero. The NASA COBE satellite detected the precise thermal spectrum of this radiation in 1990, earning its principal investigators the Nobel Prize in Physics in 2006. The subsequent WMAP satellite mapped its temperature fluctuations across the entire sky between 2001 and 2010. The European Space Agency's Planck satellite refined those maps to sub-degree angular resolution between 2009 and 2013. Those temperature fluctuations, variations of roughly 1 part in 100,000 across the sky, are the seeds of all structure in the observable universe. Regions slightly denser than average at the moment of recombination became gravitational wells into which matter slowly fell over hundreds of millions of years, eventually forming the first stars, the first galaxies, and the vast cosmic web of filaments and voids that characterizes the large-scale structure of the universe today. The pattern of these fluctuations is a fingerprint, a precise, mathematically analyzable fingerprint of the conditions that existed in the first fraction of a second after the Big Bang. Cosmologists can extract from it the geometry of the universe, whether space is flat, positively curved like the surface of a sphere, or negatively curved like a saddle. They can extract the relative proportions of ordinary matter, and dark energy. They can extract the age of the universe, the rate of expansion, and the total number of observable stars. The Planck data says the universe is flat, to a precision of better than 0.5%. It says the universe is 13.8 billion years old. It says there are approximately 2 trillion galaxies in the observable universe, a number revised dramatically upward from the previous estimate of 200 billion, following a 2016 analysis of Hubble Deep Field images by Christopher Consolis and his team at the University of Nottingham. 2 trillion galaxies, each containing on average hundreds of billions of stars. And yet, that entire structure, 2 trillion galaxies, hundreds of trillions of stars, the full web of cosmic filaments stretching across 46 billion light-years of observable space, represents less than 5% of what the universe actually contains. The Hubble constant is the number that describes how fast the universe is expanding, specifically how many kilometers per second a galaxy recedes from us for every megaparsec of distance between us and that galaxy. 1 megaparsec equals approximately 3.26 million light-years. For decades, measuring the Hubble constant precisely was considered one of the central goals of observational cosmology. The Hubble Space Telescope was named in part in honor of Edwin Hubble, the astronomer who first measured cosmic expansion in the 1920s using Cepheid variable stars in nearby galaxies. The Hubble Space Telescope's key project, completed in 2001, measured the constant at 72 kilometers per second per megaparsec with an uncertainty of about 10%. Subsequent measurements using type Ia supernovae refined this to approximately 73. The Planck satellite's measurement of the cosmic microwave background, meanwhile, independently derived a value of approximately 67.4. 73 versus 67.4. A difference of about 8%. In everyday terms, that sounds minor. In precision cosmology, it is a catastrophe. Both measurements use independent, well-tested methods. Both have been verified multiple times by separate research teams using separate instruments. Both cannot be correct simultaneously, not if the standard cosmological model is internally consistent. This discrepancy has a name: the Hubble tension. It has been growing more statistically significant with each new dataset for over a decade. As of the most recent analyses using James Webb Space Telescope data, the tension persists. It is not resolved. If anything, Webb's measurements of Cepheid variable stars in nearby galaxies have strengthened the higher value, making the discrepancy with the Planck result more difficult to dismiss as systematic error. Something in the standard model is wrong, or something in one of the measurement chains is wrong, or the possibility that keeps certain cosmologists awake. The universe behaved differently in its early history than the standard model assumes, and dark energy is not a constant, but a dynamic field that has evolved over cosmic time. That last possibility has a name too: quintessence, a hypothetical form of dark energy whose density changes as the universe expands, unlike the cosmological constant, Einstein's original lambda term, which remains fixed at the same energy density regardless of the size of the universe. Einstein introduced the cosmological constant in 1917 to make his equations of general relativity describe a static universe. He abandoned it when Hubble's observations confirmed cosmic expansion, calling it the greatest blunder of his career. Decades later, the supernova teams discovered that something very much like the cosmological constant appears to be real after all, except that its measured value is approximately 120 orders of magnitude smaller than the value quantum field theory predicts for the energy density of empty space. 120 orders of magnitude. That is a 1 followed by 120 zeros. It is the largest discrepancy between theory and observation in the history of physics. Physicists call it the cosmological constant problem. Some call it the vacuum catastrophe. It has been unresolved since Steven Weinberg first clearly articulated it in 1989. Every major observatory built since then has been gathering data that constrains, but has not yet solved, this fundamental incompatibility between quantum mechanics and general relativity, the two most successful theories in the history of science, which cannot both be completely correct because they fundamentally disagree about the nature of empty space. $93 billion. 50 years of instruments, launches, failures, servicing missions, and triumphs. And the central question of modern physics remains open. Not because the science has failed, because the universe is harder than we imagined. What happens when the James Webb Space Telescope, armed with the deepest infrared sensitivity ever deployed in space, turns toward the most ancient structures in the observable universe? And the galaxies it finds there are not behaving the way 13 billion years of accepted physics says they should? The universe did not begin in darkness. It began in light so intense, so dense, so incomprehensibly energetic that the concept of empty space had no meaning. In the first fractions of a second after the Big Bang, the entire observable universe, everything that would eventually become 2 trillion galaxies, hundreds of trillions of stars, and every atom of every element that has ever existed, was compressed into a volume smaller than a proton. The temperature at that moment exceeded 10 to the power of 32 degrees Kelvin. That number has a name: the Planck temperature. It is the theoretical upper limit of heat permitted by the known laws of physics, the point at which our current equations break down entirely, and general relativity ceases to describe reality in any coherent way. Physics has no model for what existed before or at that moment. None. What it does have is an extraordinarily precise model of everything that happened afterward. Starting from approximately 10 to the negative 43 seconds after the Big Bang, 1 Planck time unit, the smallest meaningful interval of time that physics currently recognizes, the universe can be described mathematically with remarkable accuracy. The timeline that follows is not speculation. It is the product of decades of particle accelerator experiments, satellite observations, and theoretical work across multiple independent branches of physics, all converging on the same sequential description of cosmic evolution. In the first 10 to the negative 36 seconds, the universe underwent a period of exponential expansion called inflation. This is not the same expansion that Hubble measured, and that continues today. Inflation was something categorically different, a phase transition in the fabric of space-time itself, driven by a hypothetical energy field called the inflaton, during which the observable universe expanded by a factor of at least 10 to the power of 26 in an almost immeasurably brief interval. To put that in human scale, if a single atom were to expand by the same factor that the universe expanded during inflation, that atom would end up larger than the currently observable universe, larger than 46 billion light-years across. The evidence for inflation is not direct. No instrument has detected an inflaton field. What the evidence supports is the set of conditions inflation would have produced: a spatially flat universe, a nearly uniform temperature distribution across the cosmic microwave background, and a specific spectrum of density fluctuations with a particular mathematical shape called a scale-invariant Harrison-Zeldovich spectrum. Every precision measurement of the cosmic microwave background, from COBE to WMAP to Planck, has confirmed these predictions to high statistical significance. The universe looks exactly as inflation predicts it should look. That is powerful evidence, even without direct detection of the mechanism. After inflation ended, the energy stored in the inflaton field converted into a dense, hot plasma of fundamental particles. This process is called reheating. The universe at this stage contained quarks, gluons, electrons, neutrinos, and photons in thermal equilibrium, a state called the quark-gluon plasma. Particle accelerators on Earth have recreated this state briefly at CERN's Large Hadron Collider, in collisions between heavy lead ions that generate temperatures exceeding 5.5 trillion degrees Kelvin. The quark-gluon plasma that results lasts for approximately 10 to the negative 23 seconds before the quarks recombine into protons and neutrons. In the early universe, this phase lasted until approximately 10 microseconds after the Big Bang. At 1 second after the Big Bang, the universe had cooled enough for a critical process to begin: neutrino decoupling. Neutrinos are subatomic particles with almost no mass and no electric charge, interacting with matter only through the weak nuclear force and gravity. At the temperatures of the first second, neutrinos were in constant interaction with electrons and photons. As the universe cooled below approximately 10 billion degrees Kelvin, those interactions became too infrequent to maintain thermal equilibrium. The neutrinos decoupled, they stopped interacting, and have been traveling freely through the universe ever since. Right now, approximately 336 neutrinos from the Big Bang pass through every cubic centimeter of space, including through your body, every second. They are undetectable by any current instrument. They are everywhere. Between roughly 3 minutes and 20 minutes after the Big Bang, the universe passed through a phase called Big Bang nucleosynthesis. The temperature had dropped to approximately 1 billion degrees Kelvin, hot enough for nuclear fusion reactions, but not so hot that the resulting nuclei would be immediately torn apart. During this window, protons and neutrons fused to form the nuclei of helium-4, helium-3, deuterium, and trace amounts of lithium-7. The ratios in which these light elements were produced are precisely predicted by the standard model of cosmology and have been confirmed by spectroscopic measurements of ancient, chemically unprocessed gas clouds. The universe emerged from nucleosynthesis with a composition of approximately 75% hydrogen and 25% helium by mass. Every element heavier than lithium, every carbon atom in every living organism, every iron atom in every planetary core, every gold atom in every piece of jewelry, was forged later, inside stars. The stellar nucleosynthesis process was worked out in detail by 4 physicists, William Fowler, Fred Hoyle, and Jeffrey and Margaret Burbage, in a landmark 1957 paper known simply as B2FH, after their initials. It described how stars build heavier elements through successive stages of nuclear fusion, starting with hydrogen burning in their cores. A star like our Sun fuses approximately 620 million metric tons of hydrogen into helium every single second. It has been doing this for approximately 4.6 billion years. It will continue for roughly another 5 billion years before its core exhausts its hydrogen supply and the star evolves off the main sequence. Stars more massive than about 8 solar masses follow a different evolutionary path. They burn through hydrogen faster. A star of 20 solar masses may spend only 8 million years on the main sequence, compared to 10 billion for our Sun. And when hydrogen is exhausted, gravity compresses the core further, raising the temperature until helium fusion ignites. Helium fuses into carbon and oxygen. When helium is exhausted, carbon ignites, fusing into neon, sodium, and magnesium. Neon burns to oxygen. Oxygen burns to silicon and sulfur. Silicon burns to iron. Iron is where fusion stops. The fusion of elements up to iron releases energy. It is exothermic. Fusing iron requires energy input. It is endothermic. When a massive star's core fills with iron, fusion ceases. The core, which has been supported against gravitational collapse by the outward pressure of fusion reactions, loses its support in less than 1 second. Gravity wins. The iron core collapses at approximately 1/4 the speed of light, reaching nuclear density, approximately 394 million metric tons per cubic centimeter, in less than half a second. At that point, the strong nuclear force halts the collapse abruptly. The infouling outer layers of the star rebound off the stiffened core, generating a shock wave that propagates outward through the star and drives a supernova explosion. The energy released in a core collapse supernova is approximately 3 × 10 to the power of 46 joules. 99% of that energy is carried away by neutrinos in the first 10 seconds. The visible light of the explosion, the spectacle that can outshine an entire galaxy of hundreds of billions of stars for weeks, represents just 1% of the total energy released. The neutrino burst from a supernova was directly detected for the first and only time on February 23, 1987, when a massive star in the Large Magellanic Cloud, a satellite galaxy of the Milky Way approximately 160,000 light-years away, exploded. Neutrino detectors in Japan, the United States, and the Soviet Union simultaneously registered a burst of 25 neutrinos over a 13-second window. 25 particles out of the 10 to the 58 neutrinos the explosion released detected across 3 continents. The supernova, designated SN 1987A, is still observable today as an expanding ring of glowing gas and has been continuously monitored by every major space telescope since its discovery. The remnant at the center of SN 1987A is almost certainly a neutron star. Neutron stars are the collapsed cores of massive stars that did not quite reach the mass threshold required to form a black hole. They are composed almost entirely of neutrons packed to nuclear density, typically spanning approximately 20 kilometers in diameter, roughly the width of a mid-sized city, while containing between 1.2 and 2.3 times the mass of our entire Sun. The density is so extreme that a single teaspoon of neutron star material would weigh approximately 4 billion metric tons on Earth. The gravity at the surface is approximately 200 billion times stronger than Earth's surface gravity. Some neutron stars rotate at extraordinary speeds. The fastest known pulsar, PSR J1748-2446 AD, located approximately 18,000 light-years away in the constellation Sagittarius, rotates 716 times per second. Its equatorial surface moves at approximately 24% of the speed of light. These objects were first detected in 1967 by Jocelyn Bell Burnell, a graduate student at Cambridge University, who noticed a strange, perfectly regular radio pulse in her data, repeating every 1.337 seconds. The regularity was so precise that her supervisor, Anthony Hewish, initially noted the signals in his log with the half-serious designation LGM-1, Little Green Men. The possibility of an artificial origin was genuinely, briefly considered. It was not artificial. It was the most precise natural clock in the universe. Hewish received the Nobel Prize in Physics in 1974 for the discovery. Bell Burnell did not. The omission remains one of the most discussed controversies in the history of science awards. When 2 neutron stars orbit each other in a binary system, they lose energy to gravitational wave emission and spiral inward. In October 2017, the LIGO and Virgo gravitational wave detectors simultaneously registered the merger of two neutron stars approximately 130 million light-years away in the galaxy NGC 4993. The event, designated GW1708 Zion, lasted approximately 100 seconds in the detector frequency band. Within 2 seconds of the gravitational wave signal ending, NASA's Fermi Gamma Ray Space Telescope detected a short gamma-ray burst from the same location. Within 11 hours, ground-based optical telescopes had identified a rapidly brightening and fading light source, a kilonova, at the precise coordinates. The spectroscopic data from that kilonova confirmed for the first time directly that neutron-star mergers produce heavy elements through a process called rapid neutron capture, or the R process. The collision synthesized gold, platinum, uranium, and dozens of other heavy elements in quantities estimated at several times the mass of our Earth, scattered across interstellar space in the debris of the explosion. The gold in every ring, every circuit board, every gold reserve on Earth was forged in collisions like that one. Not in the cores of ordinary stars, but in the catastrophic merger of two dead stellar remnants spiraling together over millions of years. Every atom of gold that has ever existed came from a collision between two neutron stars. The iron in your blood was forged inside a star that exploded before the sun was born. The calcium in your bones was synthesized in stellar cores across multiple generations of stellar evolution. The oxygen in every breath was produced in the last few thousand years of life of massive stars that detonated billions of years before the Earth formed. The universe built you from the inside of dead stars, scattered you across interstellar space over billions of years, and assembled you here, on this planet, at this moment. And the mechanism by which it did all of this, the precise sequence of nuclear reactions, gravitational collapses, shock waves, and merger events that produce the chemical complexity of a living world, was not designed to be understood. It was not designed at all. It simply happened. Over 13.8 billion years, one law of physics at a time, which raises the question that the James Webb Space Telescope is now forcing physicists to confront directly. If we understand the physics well enough to trace every atom in your body back to its stellar origin, why can't we explain the galaxies that formed when the universe was less than 3% of its current age? In the summer of 2022, the first full-color science images from the James Webb Space Telescope were released to the public. NASA Administrator Bill Nelson stood at a podium at the White House and described what the world was about to see. The images were extraordinary, technically, aesthetically, scientifically. A galaxy cluster called SMACS 0723, located approximately 4.6 billion light-years away, served as a gravitational lens, its immense collective mass bending and magnifying light from galaxies far beyond it, producing distorted arcs of ancient light that Webb's infrared detectors resolved with unprecedented sharpness. In that single image, some of the background galaxies had redshifts placing them at distances corresponding to light travel times of over 13 billion years. The scientific community had waited 30 years for this instrument. The reaction when the data began to arrive in earnest was not what most expected. It was not celebration. It was confusion. Within months of the first public data releases, multiple independent research teams began publishing analyses of Webb's deep field observations. The papers converged on the same finding from different angles, using different methodologies, targeting different regions of the sky. The galaxies Webb was resolving in the very early universe, objects with spectroscopic redshifts of 8, 10, 12, and beyond, corresponding to epochs when the universe was between 300 and 600 million years old, were massive, structured. Some showed evidence of already formed stellar populations billions of years old relative to the time of observation, which is physically incoherent under the standard model. A stellar population billions of years old cannot exist inside a universe that is itself only a few hundred million years old. One of the most discussed early findings involved a galaxy designated JADES GS-Z30, identified in the JWST Advanced Deep Extragalactic Survey. Its redshift placed it at approximately 320 million years after the Big Bang, making it, at the time of its confirmation, the most distant galaxy ever spectroscopically confirmed. It exists. It emits light, it has a measurable stellar mass, and it should not have had time to form under the gravitational assembly processes described by the lambda CDM model. The lambda CDM model, lambda for the cosmological constant representing dark energy, CDM for cold dark matter, has been the standard framework of cosmology since the late 1990s. It describes a universe in which structure grows hierarchically. Small perturbations in the density of dark matter in the early universe gradually collapsed under gravity, forming dark matter halos. Gas fell into those halos, cooled, fragmented, and formed the first stars. Those first stars enriched the surrounding gas with heavier elements through supernova explosions. Over hundreds of millions of years, small proto-galaxies merged and accumulated mass, building progressively larger structures. The key word in that sequence is gradually. The model has a built-in timescale. Gravity works at a specific rate. Gas cooling has physical constraints. Star formation efficiency has observed upper limits. The model is not vague. It makes quantitative, testable predictions about how many galaxies of a given mass should exist at each epoch in cosmic history. Webb's observations exceeded those predictions by factors that ranged, depending on the specific mass range and redshift bin analyzed, from 10 to 100. Not 10 or 100% above predictions, 10 to 100 times the predicted number of massive luminous galaxies in the early universe. Astrophysicist Alison Kirkpatrick at the University of Kansas, one of the researchers who contributed to early Webb galaxy analyses, described the findings in a widely cited statement as causing an existential crisis for cosmology. The phrase was precise rather than dramatic. It reflected a genuine structural problem in the theoretical framework. The response from the theoretical community divided along two lines. The first position held that the observations were real, but the apparent contradiction could be resolved by revising the astrophysical models of how stars form within galaxies, rather than revising the cosmological framework itself. Star formation efficiency in the early universe might have been substantially higher than at later epochs. Early galaxies may have converted a much larger fraction of their available gas into stars, faster than models predicted. Feedback processes, the winds and radiation from massive stars and active galactic nuclei that typically suppress star formation by heating and expelling gas, might have operated differently or less efficiently in the early universe's denser, more turbulent conditions. The second position was more radical. It held that the cosmological framework itself required modification. If the hierarchical assembly model cannot produce galaxies of observed mass and structure in the observed time frame, even after generous revisions to star formation efficiency, then either dark matter does not behave the way lambda CDM assumes, or the initial conditions of the universe following inflation generated more concentrated density fluctuations than the standard model predicts, or the universe is older than 13.8 billion years. That last possibility is the most structurally destabilizing. The age of the universe is not a single measurement. It is the convergence of multiple independent lines of evidence. The expansion rate measured by the Hubble constant, the age of the oldest stellar populations in globular clusters, the temperature and acoustic peak structure of the cosmic microwave background. All of these converge on approximately 13.8 billion years with remarkable mutual consistency. Revising the age of the universe upward to accommodate the Webb galaxies would require explaining why all of those independent lines of evidence are simultaneously wrong in the same direction. That is not impossible. It is very hard. A separate but related observational challenge emerged from Webb's study of Cepheid variable stars in nearby galaxies. Cepheid variables are stars that pulsate in brightness, with periods directly related to their intrinsic luminosity. Another class of standard candles, used for a century as the primary rung on the cosmic distance ladder. Edwin Hubble used Cepheids to establish that the Andromeda Nebula was a separate galaxy beyond the Milky Way. The Hubble Space Telescope's key project used Cepheids to calibrate the cosmic distance scale and anchor the measurement of the Hubble constant. Webb's infrared capabilities allowed it to observe Cepheids in more distant galaxies with less contamination from crowding. The blending of light from nearby stars that can bias Hubble's optical measurements. The expectation among some astronomers was that Webb would reveal systematic errors in the Hubble measurements that would bring the local Hubble constant value down toward the Planck value of 67.4, resolving the Hubble tension. The opposite happened. Webb's Cepheid measurements confirmed the higher local value, near 73 kilometers per second per megaparsec, with no evidence of the crowding bias that had been proposed as a resolution. The Hubble tension did not shrink. It hardened. Adam Rees, one of the 3 Nobel laureates who discovered cosmic acceleration, led the Webb Cepheid study. His team's conclusion was unambiguous. The discrepancy between the early universe and late universe measurements of the expansion rate is real, is not an artifact of measurement error, and requires a physical explanation. The standard cosmological model, as currently formulated, does not provide one. The implications ramify outward. If dark energy is not a cosmological constant, but a dynamic field, its value in the early universe may have differed from its current value. Several theoretical models, including early dark energy models proposed by Mark Kamienkowski and colleagues at Johns Hopkins University, attempt to resolve the Hubble tension by introducing a brief episode of enhanced dark energy density in the early universe, around the time of matter-radiation equality, that would alter the sound horizon scale imprinted in the cosmic microwave background and shift the inferred Hubble constant upward. These models are constrained, but not ruled out. The Atacama Cosmology Telescope and the South Pole Telescope have provided data that partially tests these scenarios, with results that remain inconclusive. Meanwhile, a completely separate observational program was quietly producing data that intersected with these cosmological questions from an unexpected direction: the Laser Interferometer. Gravitational Wave Observatory, LIGO, completed its first observing run in 2015 and 16, detecting gravitational waves for the first time in history on September 14, 2015. The signal, designated GW150914, lasted approximately 0.2 of a second in the detector band and was produced by the merger of 2 black holes located approximately 1.3 billion light-years away. The black holes had masses of approximately 36 and 29 solar masses, respectively. The merger produced a final black hole of approximately 62 solar masses. The missing 3 solar masses were converted directly into gravitational wave energy, the equivalent of approximately 5.3 times 10 to the 44 joules, radiated in under a second. That energy output, for that fraction of a second, exceeded the combined luminosity of all stars in the observable universe. The detection itself was made possible by measuring a displacement of the LIGO interferometer's 4-kilometer arms of approximately 1,000th the diameter of a proton. The instrument is sensitive enough that it must correct for the gravitational pull of clouds passing overhead, the microseismic noise of ocean waves breaking on coastlines thousands of kilometers away, and quantum vacuum fluctuations in the laser light itself. It is, by almost any measure, the most sensitive measuring instrument ever constructed by human civilization. In 2017, LIGO and its European counterpart Virgo detected their first binary neutron star merger, the GW170817 event described in Act 3. In the years since, the Gravitational Wave Detector Network has accumulated a catalog of over 90 confirmed compact binary merger events, black hole mergers, neutron star mergers, and at least 2 events consistent with neutron star black hole mergers. The mass distribution of the detected black holes has itself produced surprises. Several of the merging black holes fall in a mass range between approximately 40 and 130 solar masses, a range that standard stellar evolution theory predicts should be largely empty, because stars in that mass range are expected to undergo pulsational parinstability supernovae that either destroy the star entirely or produce a much lighter remnant. The black holes are there anyway. The gap that theory predicted is populated. The mechanism that should have prevented these black holes from forming apparently did not prevent them. Either the stellar evolution models are missing something, or these black holes formed through a different channel. Repeated mergers of smaller black holes in dense stellar environments, or primordial black holes formed in the early universe before any stars existed at all. Primordial black holes. The concept has existed in theoretical physics since Stephen Hawking and Bernard Carr first explored it in 1974. If density fluctuations in the very early universe were large enough in certain regions, those regions could have collapsed directly into black holes before any star formation occurred. These primordial black holes could, in principle, range enormously in mass, from the Planck mass upward to thousands of solar masses. They would be invisible by nature, detectable only through gravitational lensing or gravitational wave emission. If primordial black holes exist in sufficient numbers, they might constitute a fraction of the dark matter. The mass range currently least constrained by observations, roughly between 1/10 and 100 solar masses, corresponds almost precisely to the mass range of the black holes LIGO has been detecting. The overlap is not proof, but it is not nothing. Every unexpected signal from every instrument points in the same direction, toward physics that is real, measurable, and not yet understood. The universe is not withholding its secrets out of complexity alone. It is exposing them, one gravitational wave, one anomalous galaxy, one unresolved tension at a time. And then, in 2023, Webb turned toward a region of sky that had been observed dozens of times before, and found something that stopped the analysis teams mid-calculation. On March 16, 2023, a team of astronomers led by Rohan Naidu at MIT published a paper that immediately circulated through every major astrophysics department in the world. It described two galaxy candidates detected by Webb, designated JD as GS Z30 and JD as GS Z14, at spectroscopic redshifts, placing them within the first 300 million years of cosmic history. The galaxies were not faint smears of uncertain photometry. They were bright, resolved. Their spectra showed clear emission lines from ionized oxygen, a heavy element that requires multiple generations of stellar nucleosynthesis to produce, present in galaxies that, under the Standard Model, should have barely begun forming their first stars. Oxygen. In the first 300 million years. The detection of oxygen at that redshift is not merely surprising. It is structurally incompatible with the lambda CDM model's predictions about the timescale of chemical enrichment in the early universe. To produce detectable oxygen in a galaxy's spectrum, massive stars must have already formed, lived their entire lives, which for the most massive stars spans only a few million years, and exploded as supernovae, seeding the surrounding gas with the products of their nuclear burning. That entire cycle must have completed not once, but multiple times to accumulate enough oxygen to register in spectroscopic data. Each generation of stars takes time to form from collapsing gas clouds. The gas must cool, the clouds must fragment, gravity must do its work. The universe at the redshift of these galaxies had simply not had enough time for that to happen. Not according to any current model of star formation operating within the lambda CDM framework at standard efficiency, and yet the oxygen line is there. Measured. Confirmed across multiple independent observations with Webb's NIR-SPEC spectrograph, an instrument capable of simultaneously obtaining spectra from up to 200 objects within its field of view, dispersing their light across wavelength ranges from 0.6 to 5.3 micrometers with a spectral resolution sufficient to distinguish individual atomic emission features. The data quality is not ambiguous. The redshift determinations are not uncertain. The oxygen is real. In 2024, Webb pushed further. The galaxy designated JD's GS Z14, confirmed through spectroscopy in a paper led by Stefano Carniani at the Scuola Normale Superiore in Pisa and published in Nature in May 2024, was confirmed at a redshift of 14.32, corresponding to a look-back time of approximately 13.5 billion years. The universe at that epoch was approximately 290 million years old. This galaxy had a stellar mass estimated at several hundred million solar masses and a physical diameter of approximately 1,600 light-years. It was actively forming stars at a rate of roughly 20 solar masses per year. 20 solar masses of new stars forming every year, in a galaxy that existed when the universe was less than 290 million years old. For comparison, the Milky Way today, after 13 billion years of stellar evolution and galaxy assembly, forms new stars at a rate of approximately 1 to 3 solar masses per year. This ancient galaxy, in the first sliver of cosmic time, was building itself faster than our mature galaxy does today. The star formation rate per unit of stellar mass already present, a quantity called the specific star formation rate, was hundreds of times higher than anything observed in the local universe. The theoretical framework scrambled to respond. Several groups proposed modifications to the standard halo mass function, the mathematical description of how dark matter halos are distributed by mass at different epochs. If dark matter halos in the early universe were more concentrated than lambda CDM predicts, gas could have cooled and fragmented into stars more rapidly. Others proposed that the initial mass function of stars in the early universe was top-heavy, skewed toward the formation of very massive stars rather than the roughly solar mass stars that dominate star formation today. A top-heavy initial mass function would produce more ultraviolet radiation per unit of stellar mass, making early galaxies appear brighter and more massive in Webb's detectors than they actually were. It would also accelerate chemical enrichment, explaining the early oxygen detections. A top-heavy initial mass function is not an ad hoc invention. It has theoretical motivation. The temperature of the cosmic gas from which the first stars formed was substantially higher than today, because the gas had not yet been enriched with heavy elements whose spectral line cooling allows gas clouds to fragment at smaller masses. Higher gas temperature means higher Jeans mass, the minimum mass of a gas cloud that can collapse under gravity, which means the first stellar generations may have been dominated by stars of hundreds or even thousands of solar masses. These hypothetical first stars are called population 3 stars. None have ever been directly observed. Webb has not confirmed a population 3 star, but several galaxy spectra at high redshift show anomalous emission line ratios consistent with the ionizing radiation from extremely massive metal-free stars, and the search is ongoing with every new observing cycle. The reionization epoch is the cosmic phase during which the neutral hydrogen gas that filled the universe after recombination was ionized by the ultraviolet radiation of the first stars and galaxies. Before reionization, the universe was opaque to ultraviolet light. The neutral hydrogen absorbed it completely. After reionization, completed by approximately 1 billion years after the Big Bang, the intergalactic medium became the largely transparent, highly ionized plasma it remains today. The precise timeline of reionization, when it started, how quickly it progressed, which sources drove it, is one of the central questions Webb was designed to address. Webb's observations of the most distant galaxies are revealing that reionization may have begun earlier than models predicted, driven by galaxies more numerous and more luminous in the ultraviolet than the standard model placed at those epochs. The ionizing photon budget, the number of high-energy photons required to reionize the intergalactic medium within the observed timeframe, may have been largely supplied by the class of compact, intensely star-forming galaxies that Webb is discovering in abundance above redshift 10. This is not a settled conclusion. It is an active research frontier, with new data arriving from every Webb observing cycle, adding constraints that continuously revise the picture. Simultaneously, Webb's mid-infrared instrument, MIRI, the mid-infrared instrument, operating between 5 and 28 micrometers, has been detecting the dust-obscured star formation in galaxies across a wide range of cosmic epochs. Dust absorbs ultraviolet light from young stars and re-emits it as infrared radiation. In the most intensely star-forming galaxies, sub-millimeter galaxies, discovered first in the late 1990s by the scuba camera on the James Clerk Maxwell Telescope on Mauna Kea, the fraction of star formation hidden behind dust can exceed 90%. Hubble was nearly blind to these objects. Webb sees through the dust. What it finds inside, dense, turbulent reservoirs of molecular gas, multiple massive star-forming clumps embedded in complex structures, confirms that the most vigorous epoch of star formation in the universe's history occurred not at the present day but at a redshift between approximately 1 and 3, corresponding to a period between roughly 3 and 6 billion years after the Big Bang. Astronomers call this period cosmic noon. The universe was building stars at a rate 10 to 30 times higher than today. Nearly half of all the stars that will ever exist in the observable universe formed during this 2 to 3 billion year window. Cosmic noon is over. The universe has been in a long, slow decline of star formation activity ever since. The rate of new star formation today is a fraction of what it was at its peak. The galaxies that remain are aging. Their stellar populations are growing older, redder, dimmer. New stars are still forming. The Milky Way produces 1 to 3 solar masses per year. But the great era of galaxy construction, the period of maximum stellar creativity in the universe's history, is billions of years behind us. The universe has already had its most productive moment. We exist in its long afternoon. The large-scale structure that emerged from cosmic noon, the web of galaxy clusters, filaments, and voids that spans the observable universe, was mapped in its modern form by the Sloan Digital Sky Survey, which over 2 decades cataloged the positions and redshifts of more than 3 million galaxies across roughly 1/3 of the entire sky. The resulting 3-dimensional map revealed a universe organized into sheets and filaments of galaxy clusters surrounding enormous underdense regions called cosmic voids, some spanning hundreds of millions of light-years across. The largest known void, the Butez void, stretches approximately 330 million light-years in diameter and contains almost no galaxies. If our Milky Way were located at the center of the Butez void, the nearest neighboring galaxy would be so distant that human civilization would not have discovered that other galaxies existed until the era of space-based telescopes. Structure on this scale should not, strictly speaking, exist. The Lambda CDM model predicts a universe that is approximately homogeneous and isotropic on scales above a few hundred million light-years, meaning that the density of matter, averaged over large enough volumes, should be nearly the same everywhere. This prediction is largely confirmed. But the boundary between structured and uniform is blurrier than the simplest models suggest, and certain observed alignments of galaxy spins and quasar polarization vectors across billions of light-years have generated quiet but persistent debate about whether the large-scale universe has preferred directions, an anisotropy, that the standard model does not accommodate. The Hercules Corona Borealis Great Wall is a candidate superstructure detected through the spatial clustering of gamma-ray bursts, spanning an estimated 10 billion light-years. If confirmed as a physically coherent structure, rather than a statistical artifact of the detection method, it would be larger than any structure permitted to form within the age of the universe under the Lambda CDM model. The finding has not achieved consensus acceptance. It has not been dismissed either. At the center of almost every massive galaxy in the observable universe sits a supermassive black hole. The Milky Way's central black hole, Sagittarius A, has a mass of approximately 4 million solar masses and was directly imaged for the first time in May 2022 by the Event Horizon Telescope collaboration, a planet-spanning array of synchronized radio telescopes that achieved an angular resolution equivalent to reading a newspaper on the surface of the Moon from Earth. The image showed the predicted bright ring of photons orbiting the black hole's event horizon and the dark central shadow where light cannot escape, precisely matching the predictions of general relativity to within measurement uncertainties. The black hole at the center of the galaxy Messier 87, imaged first by the Event Horizon Telescope in April 2019, has a mass of approximately 6.5 billion solar masses. It is so massive that the entire solar system, out to the orbit of Neptune, could fit comfortably within its event horizon with room to spare. Matter falling into it produces a relativistic jet of plasma extending at least 5,000 light-years from the galactic core, moving at apparent velocities exceeding the speed of light. A geometric illusion produced when a jet directed nearly toward the observer moves so fast that it appears to outrun its own light travel time. Supermassive black holes were present in the early universe at masses that again defy the standard formation models. Quasars, the luminous active galactic nuclei powered by matter accreting onto supermassive black holes at rates that can exceed the equivalent of 1,000 solar masses per year, have been detected at redshifts above 7, corresponding to less than 700 million years after the Big Bang. The most massive of these early quasars host black holes of several billion solar masses. Growing a black hole to several billion solar masses in under 700 million years, starting from any plausible seed mass, requires continuous accretion at the maximum physically permitted rate, the Eddington limit, for essentially the entire available time with no interruptions. Even then, the numbers barely work. Any model requiring formation from a stellar mass seed black hole of 10 to 100 solar masses cannot bridge the gap. The proposed solutions include direct collapse black holes, objects formed not from the death of individual stars, but from the direct gravitational collapse of massive gas clouds of 10,000 to 100,000 solar masses in the early universe, bypassing the stellar phase entirely, and the primordial black holes discussed previously. Neither mechanism has been directly confirmed. Both are actively searched for in current and planned observational programs. Webb has detected quasar-host galaxies at redshifts above 6 with structural complexity, disk morphologies, bulges, companion galaxies in interaction that should take billions of years to develop. The black holes at their centers are already billions of solar masses. The host galaxies are already mature. Everything in the early universe is older than it should be, more massive than it should be, more structured, more chemically enriched, more dynamically evolved than any model built before Webb predicted. The $93 billion pointed its finest instrument at the edge of time. And the edge of time looked back, ancient, massive, and completely unexpected. The observable universe extends approximately 46 billion light-years in every direction from Earth. Not because that is the edge of the universe may be infinite, and current data is consistent with both infinite and finite geometries, but because that is the furthest distance from which light has had time to reach us in 13.8 billion years of cosmic history. Beyond that horizon, space continues. Galaxies exist. Stars burn. The physical laws that govern every process described in this documentary almost certainly apply without modification. We simply cannot see that far. The information has not arrived yet. That boundary, the cosmic horizon, is not a wall. It is a delay. Every photon that enters a telescope on Earth has been traveling for some fraction of the age of the universe. The light from the sun is 8 minutes old when it reaches us. The light from the nearest star system, Alpha Centauri, is 4.24 years old. The light from the Andromeda Galaxy left its source approximately 2.5 million years ago, when the genus Homo was in its earliest stages of emergence on the African continent. The light from the most distant galaxies Webb has confirmed spectroscopically left its source when the universe was less than 300 million years old, before the Earth existed, before the Sun existed, before the Milky Way had assembled into anything resembling its present form. Looking outward is looking backward. Every observation is an act of archaeology conducted at the speed of light. This is not metaphor. It is the direct consequence of the finite speed of light, 300,000 kilometers per second, combined with the scale of the universe. When the Event Horizon Telescope imaged the shadow of Sagittarius A, it captured photons that had been orbiting within a few Schwarzschild radii of a 4 million solar mass black hole at the center of our own galaxy, 26,000 light-years away. Those photons were 26,000 years old when they arrived at the telescope array. The light that produced that image left its source before the last ice age ended on Earth. The Schwarzschild radius of a black hole, the radius of the event horizon, the surface of no return, is defined by the formula Rs2Gmc2R SEC22Gm, where G is the gravitational constant, M is the mass of the black hole, and C is the speed of light. For Sagittarius A, this works out to approximately 12 million kilometers, slightly less than the diameter of our Sun. For the black hole at the center of M87, the event horizon radius is approximately 20 billion kilometers, nearly 5 times the average distance between the Sun and Neptune. An object crossing that horizon would experience no locally dramatic event. The curvature of spacetime at the event horizon of a sufficiently massive black hole is gentle enough that a hypothetical observer falling through it would notice nothing unusual at the moment of crossing. No wall, no flash of light, no physical marker of the transition. The point of no return is invisible from the inside. What happens beyond the event horizon is, in the most literal scientific sense, unknown. General relativity predicts that all infalling matter is drawn toward a singularity, a point of infinite density at which the equations of the theory cease to produce finite, meaningful outputs. Singularities are not physical predictions. They are mathematical signals that a theory has reached the boundary of its domain of validity. The singularity at the center of a black hole marks the precise location where general relativity fails, where a complete theory of quantum gravity, which does not yet exist, would be required to describe reality. Every black hole in the universe contains at its center a point where our best physical theory stops working. There are an estimated 40 million black holes of stellar mass in the Milky Way alone. Each one is a location where the known laws of physics are incomplete. Stephen Hawking demonstrated in 1974 that black holes are not perfectly black. Quantum mechanical effects near the event horizon produce a slow thermal radiation, now called Hawking radiation, that causes black holes to lose mass over cosmological timescales. A stellar mass black hole of 10 solar masses would take approximately 2 times 10 to the power of 71 years to evaporate completely through Hawking radiation. The current age of the universe is approximately 10 to the power of 10 years. The evaporation timescale of a stellar black hole is 10 to the 61st power times longer than the current age of the universe. These objects are, for all practical purposes in the current epoch of cosmic history, permanent, but not eternal. Nothing in the universe is eternal. The future of the universe, extrapolated from the physics currently understood, follows a sequence of transitions across timescales so vast that human intuition provides no useful frame of reference. Within approximately 5 billion years, the sun will exhaust its core hydrogen supply and expand into a red giant, engulfing Mercury, Venus, and possibly Earth, before shedding its outer layers as a planetary nebula and leaving behind a white dwarf. The Milky Way will collide and merge with the Andromeda Galaxy in approximately 4.5 billion years, a process that takes billions of years to complete, and during which individual stars almost never physically collide, because the distances between stars are so vast that 2 entire galaxies can pass through each other, largely as empty space interpenetrating empty space. On timescales of 10 to the power of 14 years, 100 trillion years, the last low-mass red dwarf stars will exhaust their fuel and fade. Star formation will have ceased everywhere, as the supply of cold gas available for gravitational collapse will be exhausted. The universe will enter what physicists call the degenerate era, a cold, dark expanse populated by the remnants of stellar evolution, white dwarfs slowly cooling toward absolute zero, neutron stars, and black holes. On timescales of 10 to the power of 37 to 10 to the power of 40 years, if proton decay occurs at the rate predicted by certain grand unified theories, all ordinary matter will have dissolved. Every atom of every planet, every white dwarf, every neutron star will have decayed into radiation and lighter particles. The observational evidence for proton decay has not yet been found. Experiments at the Super Kamiokande detector in Japan have placed the proton lifetime at greater than approximately 10 to the 34th years for the dominant decay modes. The process may or may not occur. If it does not, ordinary matter persists longer, but not forever. On timescales of 10 to the power of 67 to 10 to the power of 100 years, the stellar mass black holes will have evaporated through Hawking radiation. The supermassive black holes at galactic centers will persist longer. A black hole of 1 billion solar masses takes approximately 10 to the power of 90 years to evaporate. Eventually, on timescales beyond 10 to the power of 100 years, they too will be gone. What remains is a universe of maximum entropy, thermal equilibrium at a temperature indistinguishable from absolute zero, populated only by the lowest energy particles, photons, neutrinos, electrons, and positrons so dilute and so cold that no further thermodynamic work is possible anywhere in the universe. This state has a name: the heat death of the universe. It was first described thermodynamically by Lord Kelvin in 1852, more than a century before anyone understood the large-scale structure of the cosmos or the existence of dark energy. The concept predates Einstein's general relativity, quantum mechanics, and the discovery of cosmic expansion. It was arrived at through the second law of thermodynamics alone. Entropy in an isolated system never decreases. A universe evolving for long enough will reach maximum entropy. From that state, there is no return. No fluctuation large enough to restart the process of structure formation can occur on any timescale that physics permits. The universe will end not in fire, but in silence, not in a dramatic collapse, but in a final, complete, featureless equilibrium. The thermodynamic endpoint of 13.8 billion years of structure, complexity, and light. Against that backdrop, the $93 billion spent by NASA takes on a different weight. Not because the money bought certainty, it did not. Not because it answered the final questions, it has not, and it will not, because the final questions are not the kind that close, but because it bought something rarer and more durable than answers. It bought precision. It bought the Voyager probes crossing the heliopause and transmitting at 20 watts from 23 billion kilometers. It bought the repair of a 2.2 micrometer flaw in a mirror and the subsequent discovery that the universe's expansion is accelerating. It bought the gravitational wave detector sensitive enough to measure a displacement of 1,000th the diameter of a proton and the confirmation that gold was forged in the collision of dead stars. It bought the infrared eye that looked back to within 300 million years of the beginning of everything and found galaxies that should not exist, massive, structured, chemically enriched, already ancient. Each of those instruments was built by people who understood on some level that they would not live to see the final answer. The physicists who designed LIGO in the 1980s and 90s knew the first detection might come after their careers ended. The engineers who assembled Webb's 18 mirror segments knew the telescope's full scientific return would unfold across decades of observation by scientists not yet born when the project began. The astronomers who analyzed the first Hubble Deep Field images in 1995, revealing thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length, knew that they were opening a window that would take generations to fully look through. Science at this scale is not a transaction. It is not a project with a completion date. It is a commitment made by a civilization to its own future. A decision that the universe is worth understanding, that precision matters, that the act of measuring reality with increasing accuracy is itself a form of meaning, independent of any immediate application. The James Webb Space Telescope has a planned operational lifetime of 20 years, though it carries sufficient fuel to extend that. Its successor is already in early planning stages, the Habitable Worlds Observatory, a large ultraviolet, optical, and infrared telescope proposed to NASA's Decadal survey, designed specifically to directly image Earth-like planets around nearby stars and search their atmospheres for biosignatures, molecular oxygen, methane, water vapor, the chemical fingerprints of biology. If funded and built on the current projected schedule, it could be observing by the mid-2040s. The next instrument will see further, measure more precisely, find new anomalies that the current model does not predict. The process does not end. 4.5 billion years ago, a cloud of gas and dust in one spiral arm of an unremarkable galaxy contracted under gravity. At its center, a star ignited. Around it, the residual disk of gas and dust coagulated into planets. On the third planet, liquid water pooled. Chemistry occurred. Over the course of billions of years, self-replicating molecular systems emerged, diversified and complexified into organisms capable of perceiving their environment. One lineage of those organisms developed, over a period of a few 100,000 years, the cognitive architecture necessary for abstract reasoning, cumulative knowledge transmission, and mathematical description of physical reality. Those organisms built telescopes and pointed them at the edge of time. The universe is not aware of this. It does not acknowledge it. It continues expanding, accelerating, cooling toward its thermodynamic end regardless of whether anything within it notices or understands. The galaxies at redshift 14 do not know they have been found. The black holes do not know they have been imaged. The gravitational waves from a neutron star merger 130 million light-years away passed through the Earth for the last time long before the instrument that detected them existed. But the measurement happened. The data is real. The number exists. 1.3 billion years ago, two neutron stars collided. 130 million years later, the gravitational wave from that collision reached a detector built by human beings on a small rocky planet orbiting an average star. We measured it. to within 1,000th the diameter of a proton. That is what $93 billion bought. Not the answer, the question made precise.